So what's the very last thing in our notes? I want to start off with that.
The resonance catastrophe, you assigned a homework on it.
Good. Anybody try that yet? No.
Not sure if I got all this correct.
Did you? What happened? Was there a catastrophe? I'm going to put that up there. So, because we're doing driven oscillations, and that formalism is very interesting.
Taking the limit, you end up having to do a Hospital's rule, which gets you an I out in front.
But remember but we want the imaginary part. That could be the right thing. Let me go back to that. So we have x second derivative plus omega naught squared x equals f of t over m. C is x dot plus I omega naught x. So when we're done, the x that we're looking for is going to be the imaginary part of this complex function divided by omega naught. Because remember, the imaginary part is the part right here in the red bracket, right? So the C of t here was e to the I omega naught t integral 0 to t. And we're going to let the initial condition be 0. So what do we have here? F of t over m minus I omega naught t dt. These are integration variables. And we'll leave off the initial condition, like I said. And then for this problem, this f of t was equal to f naught cos omega t. Right? F naught cos omega t. And I even said to go ahead and write this in this form, 1/2 e to the I omega t plus e to the I minus I omega t. So we have the cosine in that form. We put that into this integral, and we're going to have those e to the I omega minus omega naught, e to the I negative omega plus omega naught. So that one of those, when we do the integration, is going to have an omega minus omega naught in the denominator, right? And that's where you have to use L'Hopital's rule, or you can do an expansion. So all I have to really say on this one, you just have to be really careful, with all of your variables and signs. And I'll just state the result is that your x of t is going to be proportional to t times a, so you're going to bring out a t and times a trig function. In fact, I think it'll be t sine, it'll come in as t sine omega t, and this is when omega goes to omega naught. So this is the proportionality you're going to have in here. And let me recommend doing this. You're going to have some constant in front. Go ahead and factor in and out, or multiply in and factor out an omega t, sine omega t. That's always a good practice to do. You don't want the t hanging out there alone, because the omega t combination is dimensionless. Right? And so then what you have in front of this has the dimension of a length. Right? So that's always a good practice. And even at this stage, we can see something interesting. Namely, for very small t, you're going to have a t here and a linear t there as well, right? Small t for the sine. And so it's growing as t squared for the very small times, which is how something grows if you apply a force to it. Right? T squared So it'll have that property, and this is the resonance catastrophe because it's growing uncontrolled. Well, it's just growing linearly in time, and it gets too large. So I brought that resonance demo in the other day, right? And that's what you're seeing. So anyway, very interesting problem. And yeah, if you're careful with it, nothing can go wrong. And I'll just plus some other stuff, be some other stuff in there as well. But yeah, that's when you take the imaginary part and divide by omega naught. And like I said, this is always a good combination. In fact, didn't I have a problem if f of t is a times t? You might do a similar thing in your result as well. In terms of multiplying it by a frequency so that you have these two-dimensional lines. Okay, so those are the driven oscillations. This was in general, this is when we drive it with a cosine. And now we're going to go back to the damped driven oscillations and drive them with a cosine as well. So this kind of leads to this is one way to see the resonance phenomenon. And that here the amplitude grows. Okay, we'll see it in a different way in what follows. Okay, so good. I'm going to erase this. Well, I can use this section here. So next, damped driven oscillations. So what we have here, we can convert it. Okay. So here's what we'll have. Plus 2 gamma x dot plus omega naught squared x equals f of t over m. I gotta say a couple things about this before we start calculating. Namely, this is a linear differential equation. Linear differential equation. And it comes from the study of small oscillations. Okay, small oscillations, comma, from small stuff we just had on the board a minute ago, oscillations. And that graph I just had on the board, remember I said if the oscillations are large enough, they would no longer be harmonic. And here, if the oscillations become large enough because they're growing in time, then an actual physical system is going to be driven right out of its quadratic potential, and it will also no longer be harmonic oscillations. But at this point, the math has no idea of that, right? This is just growing indefinitely because it's just the idealized system. But this is where they come from. They come from small oscillations, so they're supposed to stay small. Point is, this thing grows, and that's why it's a catastrophe too, right? Eventually the thing breaks if you drive it too hard. So the other thing about the small oscillations, or the linear differential equation now, has to do with the complex numbers. So if you do linear operations on complex numbers, you can interchange the taking of the real part and the imaginary part with the operation itself. Okay. So that's why when we study this, we're going to start off with complex numbers. We've done that before. And we'll take the real part when we're all done. Okay. If these were nonlinear operations, you couldn't do that. You can with linear operations, with nonlinear operations, you can't. We'll come back to that when we study, or when we discuss complex numbers, but that has to be stated. So let's have a look. This, by the way, this can be done with that formalism we just used, but it's no longer as transparent. That's why we did this one with the undamped oscillations. What we're going to do here is start out with the cosine function. But we don't get a resonance catastrophe ever because we have the damping. So let's go have a look here. So we're gonna let f of t equal f naught cos omega t, and we don't have to worry about the phase right now. That's going to be the f naught times the real part of e to the I omega. So remember, this is the driving force, and if we implement that right here, now we have x second derivative, 2 gamma, x first derivative, omega naught squared x. You know, I should have, just for the record, reminded us here, the 2 gamma was equal to the b divided by m. And of course, the omega naught squared was equal to the a divided by m, right, when we started out there. So yeah, here we are, equals f naught e to the I omega t. So everything is complex now. Okay? Everything can be complex because we're driving, we have a complex function right here. We can do all of our linear operations, take the real part when we're all done. So what we do here is a trial solution. Is we actually have to do a brief discussion of the solution x of t equals x homogeneous of t plus x inhomogeneous of t. In other words, the general solution is a solution to the problem where the right side is equal to 0 plus a solution of the entire thing here. Because say I find a solution to this differential equation, and that would be this one. Then if I add a solution to just, well, the left side equals 0, that trivially solves the entire differential equation. Because then I differentiate this one, it gives me a 0, and I differentiate this one, it gives me f naught over 2. Okay. So this solution we actually know. So this solution we've been studying already. I'll abbreviate that like that, equals some constant a cos for the underdamped root omega naught squared minus gamma squared e plus some kind of an alpha of time. Actually, back up there. A e to the minus gamma t. Good, actually, before we pursue this too far, we have to remind ourselves that that's right. That was the solution without the driving force. You've got your oscillator, and you graph this thing, you're roughly seeing it decay exponentially after so and so many oscillations. So that's the one we solved the other day, and it's still part of the solution. It's still part of the solution. And if you take that and this one we're about to work on, it's kind of complicated. But the point is, if you wait long enough, this one damps out, and you're only left with this one. Okay? So this is called the transient solution. And what we're after is the long time behavior from driving a system. So this is transient because it's damped out exponentially, so you wait long enough, this one's gone, and you just have this one. Okay, so, yeah, we studied this one before. Transient. Transient just means it gets damped out. Okay, so let's look at this solution of the inhomogeneous equation. And we just do a trial solution for x inhomogeneous, and what we do is this. X of t, I'm going to give it a subscript right now. It's going to be a e to the I omega t. That's going to be the solution. This amplitude and this one have nothing to do with each other. Okay? It's just this is a different one with a tilde on it. Now that's an interesting statement because what I'm saying is if I wait long enough, this damped system is simply moving exactly with the driving force. But the thing is, this is complex, and all of the interesting physics is actually going to be in this letter A that we're going to have to study. So let me write that down. So here, A is complex amplitude. And this trial solution, if it works, it says that this oscillating system is simply going to, oscillate with the same frequency that I'm driving it with. It's going to be locked into that. So the complex amplitude. So I know we got a little time. We'll set this up now. But you'll see, this thing itself is going to have a pretty interesting form. So what we do is we take this into this differential equation, okay? And I'll name this double star into single star, which is this. What do we get? Two derivatives. Well, let me write a bit of this explicitly. So we've got x of t equals a e to the I omega t. X dot of t is equal to I omega a e to the I omega t. Second derivative. Take another derivative down, we get another I omega, so I omega squared. So that's why this is so effective. We're just going to do this differential equation now. We're going to have I omega squared from the two derivatives. So we're going to have plus 2 gamma I omega from the first derivative plus omega naught squared. And those are all x here. So a e to the I omega t equals f naught e to the I omega t. So that's taking this trial solution into a differential equation. And I'll stress again, this frequency is the natural frequency of the system, the omega naught. This is the driving frequency. I should have brought that all-time device back to class. That I had on Wednesday. But the natural, when we had those balls on the stick, so the natural frequency was whatever their frequency that you see there. The driving frequency was us pushing the thing, okay? And the idea is we can imagine having a machine that's doing this. We just dial this omega in from really small all the way to really large. And the natural frequency is just somewhere in that range. That's what we're going to do. But first we have to evaluate this a bit. So what we have to do is, you know, actually I put this here, our goal is to calculate A. Okay. And here it is. Got a minute. So how do we solve for A? We have, first of all, to multiply this out plus 2 gamma I omega plus omega naught squared times A is equal to F naught. And let's go use the board over here. All the practice we've been getting with complex numbers comes in handy. So we have the amplitude F naught divided by, let's write it this way, omega naught squared minus omega squared, put that in parentheses, plus I times 2 gamma omega. So we're dividing by a complex number. And you guys remember the strategy for dealing with this? We multiply it by a particular one, namely, we're going to multiply it by omega naught squared minus omega squared minus I 2 gamma omega. And down here the same thing, omega naught squared minus omega squared minus I. So we already have a result here. Number times its complex conjugate, so we've got omega naught squared minus omega squared squared plus 4 gamma squared omega squared in the denominator, and the numerator, go put this out in front of it. In the numerator, we have what was up there, omega squared minus I times 2 gamma omega. That's as far as I'm going to get for today. Let's see if we can say a word or two about this. So right now, the amplitude is explicitly the complex number that we were talking about. Since it's a complex number, we can write, and we will write next time around, we can write A is equal to the magnitude of A times e to the I d for some phase. X that we've been looking for, is it still up there? Yeah. Then the X of t that we'll be looking for would be A magnitude. We've got the e to the I omega t plus b. We'll leave it right there. So that's what we can do, right? With complex numbers, we can do that. We haven't done it yet, but it's possible. And if we do that, then what's the real part of this? This is a complex number, what's its real part? You just gotta go to here and use Euler's formula. It'll be this magnitude of the amplitude cosine omega t plus b. And all the physics is actually gonna be in here because we already know that we're driving it with frequency omega, right? So we started out with. But this amplitude here, you know, it's a complicated expression. It's going to be interesting to evaluate. Good, so that's what we'll do. Next Monday, though, we'll also do enough of a review because we're going to have that exam on Wednesday, right? So I think we're in good good shape. What kind of problems did we have due this week? Too late to add any more, right?
I think we have 23. Yeah.
Okay.
Last one was
Good.
catastrophe problem.
Right, residence, well, okay, that's good set.